In this video, we're going to talk about valence bond theory. This is the second of our video in this series. We talked about valence bond theory of molecules with steric number 4, which have all single bonds. In this video, we're going to talk about molecules that have steric number 3 and what happens when we have a double bond in valence bond theory. And the molecule we're going to use as our example will be formaldehyde, which is CH2O. So the Lewis structure is shown here. And Lewis theory tells us that this is made of two CH single bonds plus a CO double bond. Single bonds are formed from 2 valence electrons. Double bonds formed from 4 valence electrons. The molecular geometry of formaldehyde is trigonal planar. All the atoms lie in one plane. And for the sake of discussion, we're going to consider this to be the XY plane that all these atoms lie in. And the bond angles are all about 120 degrees. So that's our starting point, and two things that we have to be able to fit within our valence bond description of the formaldehyde molecule. And we're going to focus here mostly on the bonding between carbon and oxygen, that's CO double bond. In the previous video, we described what CH single bonds look like. So we're going to spend a little bit less time on that, but let's start with our quantum theory of the two atoms involved, carbon and oxygen. And we're only going to focus on the valence electrons, since from a bonding perspective, that's what we care about. So carbon with its 4 valence electrons is like the diagram on the left, showing the valence orbitals 2s and 2p. The electrons are paired in 2s, and I have single electrons in 2 of my 3p orbitals. Oxygen with 6 valence electrons, 2 and 2s, 2 in one of the 2 p's paired up, and then 2 single electrons in my 2 remaining p orbitals. Now remember, we also are going to start with our quantum theory of bonding, and we described this with H2, and we looked at how this works for CH4 as well, but the quantum theory of bonding is that the orbitals that contribute the valence electrons to form this 2-electron bond will overlap or add together to form the bonding orbital. So for example, in the molecule H2, 2 hydrogen atoms come together, their electrons each in 1s orbitals. These combine or overlap to produce a bonding orbital that looks like this, covering both nuclei of the bonded atoms. So we call this a sigma bonding orbital, and it has the 2 electrons that are present in the bond. We also know from quantum theory the shapes of these orbitals. So the carbon 2s orbital is spherical. The carbon 2p orbitals are a pair of lobes. And remember that the carbon p orbitals have a plus orientation on one side and then a minus orientation on the other, with a node right at the nucleus in the center. So the wave function changes sign. And each of these are oriented, our 3p orbitals are oriented along the axes, x, y, and z, so they will be at 90 degrees to one another. Same is going to be true in oxygen. So the orbitals are the same. The only difference between carbon and oxygen then is the number of electrons. Now, let's just briefly look at what we said the bonding looked like from a valence bond perspective in CH4. And recall that what valence bond theory tells us is that our free carbon atom, meaning the carbon atom here, which is carbon with no other atoms around it, so just a free carbon atom completely by itself out in space, I have my valence orbitals that we showed before. But when carbon is present in the middle of a molecule like CH4, what I end up with is 4 sp3 hybrid orbitals, which are formed by linear combinations of our atomic 2s and 2p orbitals. And each one of these electrons, each one of our 4 valence electrons, sits in each of our hybrid orbitals. From there, we looked at what the hybrid orbitals look like, because they're simply a linear combination of our 2 atomic orbitals, the 2s and the 2p set. So I combine the 2s orbital, I take 1/4 of 2s, I take 3/4 of 2p, remembering that I have different signs on each side of my lobes of 2p with a nucleus here in the center. So the line in a negative way, plus to minus, with the 2p lobe on the left. and the 2s orbital will combine in a positive way with the 2p orbital on the right. So what I get is the hybrid orbital shown here in the upper right corner, where this larger lobe is a result of the end-phase combination of the plus 2s orbital combining with the plus lobe of 2p. This smaller lobe here, which is behind the nucleus again is at the center here, is not involved in bonding, and that results because I have an out-of-phase or a plus-minus combination of the 2s and 2p orbital. And my bonding orbital, each of them looks like an overlap of the sp3 hybrid with my 1s orbital. So the bonding orbital is simply the sp3 of carbon plus the hydrogen of 1s. Each of those is directed at the corners of a tetrahedron. So I end up with this picture of valence bonding in CH4. Now this orbital here represents one of my hybrid orbitals on carbon. That overlaps with one of my hydrogen 1s orbitals. I have the same thing here, and the same thing here. So that's what we developed in the last video. We're going to do something very similar with our molecule CH2O, again with our focus on the CO double bond. So to look at the bonding in that CO double bond, we need the orbital hybridization scheme for both carbon and oxygen, since we're going to look at both of those. Now what we find is that our 4 orbitals, the 2s orbital plus the 3 2p orbitals, come together in a different way this time. Now I only have 3 hybrid orbitals, each with equivalent energy, and I have 1 remaining p orbital left over. Now why does that happen? What quantum theory tells us, and this is arguments from symmetry, and we'll run into that a little bit more when we talk about molecular orbital theory, but what quantum theory tells us that it's that all the atoms lie in a single plane, which they do for CH2O, that any of the orbitals in the atoms that are perpendicular to that plane cannot participate in the hybridization process. Now, it's simply a result of the math, and again, the math is not something we're going to go into in detail, so we'll just present that result. But that's why we end up with this 2p orbital, the 2pz, which is perpendicular to the plane of the molecule that doesn't participate in hybridization. So my hybrid orbitals then are formed from 1 part s and 2 parts p. So what we call these are sp2 hybrid orbitals. The same thing is going to happen for oxygen. I have my 3 sp2 hybrid orbitals. I have my remaining 2p orbital. The only difference is for oxygen, I have 6 valence electrons. So I find that 2 of those electrons are paired in my hybrid orbital. I have 1 hybrid orbital here, which can form a bond, and I have a second hybrid orbital here that can form a bond. For carbon, I can form 4 bonds, since I have 4 individual electrons, each in separate orbitals there. Now let's look at what these sp2 hybrid orbitals look like. There isn't a whole lot of difference between those and our sp3 hybrids. Now I actually start with 1/3 of my 2s orbitals plus 2/3 of my 2p orbital set. Again, I have the same overlap, so I have a plus and a minus lobe on 2p. This is overall just a single lobe, positive. So I get positive reinforcement with the p orbital on the right, p lobe on the right, and I get negative reinforcement with the p orbital on the p lobe on the left. So what my sp2 orbital looks like is this. And this will be the lobe which extends toward each of the bonded atoms that extend from that carbon atom to form all of the sigma bonds. And the smaller lobe behind is not going to participate in bonding. And my carbon or my oxygen nucleus will be right here in the center. So let's look at what each of these individual atoms looks like after the orbital hybridization process. Now in this picture, I can't really show you this small lobe, so I'm not going to represent this in the picture that I have here. It's a little bit too busy if I include that. And all I really care about are these lobes that are the larger ones that extend toward the bonded atoms. So what the mathematics gives me is that I have 3 sp2 hybrid orbitals. I have one here, here, and here. Those are all in a single plane. They extend outward from the nucleus of the atom, which is at the center here, at 120 degrees angles. And then I have my pz orbital, which extends with one lobe above the plane. So we'll let this be our positive lobe in purple. Our gray lobe will be negative down below. That pz orbital is perpendicular to the plane. And both my carbon and my oxygen atom that come together to form this CO double bond will have this same appearance of the orbitals. So let's see how that comes together. I'm going to consider the sigma bonds, which lie in the plane, separately from the bonds that are formed from that pz orbital, which is perpendicular to the plane. So let's start with the sigma bonds first. I get an overlap in my CO double bond. I have first a single bond, which is formed by combining one of the carbon sp2 orbitals overlapping with one of the oxygen sp2 orbitals. That overlap means that these two sum together to form a bonding orbital. So in this example, the carbon atom would be here, the oxygen atom over there. So that defines one of the bonds of my CO double bond. Now let's see where that second bond of the CO double bond comes from. And that's where this pz orbital that's perpendicular to the plane of the molecule comes in. So let's look at the bonding in that second bond of the CO double bond. What that looks like is to take my pz orbital, and this is the one from carbon. This is the one from oxygen. Here's the plane of the molecule that lies right here going through the nuclei. So I can't really see that. What I'm looking now is at the pz orbitals. I have a plus lobe in purple on both the upper faces of the molecule. I have my negative lobes in gray down below. So what happens is the two plus lobes come together to form part of my pi bond. This is the second bond in the CO double bond above the plane of the molecule, and the other lobe down below, where the two minus lobes together come to form the other lobe of my pi bond. So just like a p orbital, a pi bonding orbital has two lobes. One above the plane, we'll call that plus, and the other lobe down below, we'll call that minus. Now remember, this is a single orbital, just like a p orbital is a single orbital with two lobes. A pi bonding orbital will be a single bonding orbital with two lobes. Now what happens is that I end up with 2 electrons in my sigma bond between carbon and oxygen, and I end up with 2 more electrons in this pi bond. So that's my 4 electron bond of the CO double bond that we know about from Lewis theory. Now, more generally, a double bond then will be always formed from 1 sigma bond and 1 pi bond. This is always going to be true in every case of double bonds that we encounter in valence bond theory. All right, let's come together and see what this looks like as the whole molecule. So above this line right here, I have my hybrid orbitals. So each one of my sp2 hybrids looks like this. The lobe that extends toward the atom that's going to be bonded is right there. Here is my CO single bond, the sigma bond, and here is the second, or the pi bond of the CO double bond. This is what my orbital hybridization scheme looks like, with my orange sp2 hybrids in the plane, and my pz orbital vertical to the, or horizontal to that plane, or perpendicular to that plane, with a plus and minus lobe. Okay, so here's my Lewis structure of formaldehyde. I have a 120-degree bond angle, CH single bonds. We already know how those form. Those will form from overlap of the sp2 hybrid orbital of carbon with the 1s orbital of hydrogen. And we now know what that CO double bond looks like. So let's see how that comes together. Let's look first at the sigma bonding portion in the plane. So that is formed from each of my orange sp2 hybrids. So this is an sp2 here, an sp2 here, and another sp2 here. Now the same will be true on the oxygen. So my CH single bonds are formed from overlap of the sp2 on carbon with the hydrogen 1s. This one, same thing, overlap of the sp2 hybrid orbital with the 1s on hydrogen. The sigma bond for C bonded to O is in the center here, overlap of the two hybrid orbitals. And then for oxygen, since I have this unshared pair of electrons here in the Lewis structure, I end up with the same thing in the valence bond theory of CH2O. And here's my non-bonding pairs that occupy two of those sp2 hybrid orbitals on oxygen. Okay, so that's the sigma bonding scheme in the plane. Let's look at the pi bonding scheme. So here I have my side-to-side overlap of the two positive lobes of the pz orbital, which is above the plane. Here are the minus lobes of the pz orbitals below the plane. So I get one of my lobes of the pi bond above the plane of the molecule, the other one down below. The positive above in purple, the negative down below in gray. So that overall describes the bonding in CH2O. I know what my CH single bonds look like. I know what my CO double bond looks like. Now let's extend this to the molecule C2H4. So here is the Lewis structure of C2H4. It's very similar to CH2O. So I have instead now a CH2 on the left side of the molecule right here. On the right side of the molecule I have another CH2. And these come together to form a CC double bond in between. So my two central atoms are the carbon atoms. So let's look at the orbital hybridization that occurs for each carbon. One of my carbons, the carbon on the left, is going to have its sp2 hybrid orbitals. So here's those three sp2 hybrids, plus the remaining two pz. The same is going to be true for the orbital hybridization on the second carbon. Here's my sp2 hybrid orbitals. There's the pz right here. So orbital hybridization of both of them is the same. The hybrid orbitals are formed the same way. 1/3 of 2s plus 2/3 of 2p forms one of my sp2 hybrids. Each carbon has three of those. Those come together to form this. So I have my three sp2 hybrid orbitals in the plane. I have my pz orbital with the purple lobe is plus and down below is minus. The way this comes together is to look at the sigma bonding scheme that's in the plane of the molecule, which will involve my sp2 hybrid orbitals on carbon. So let's look at that sigma bonding scheme in the plane for CH2 or C2H4. So each of my CC single bonds looks like this. The sigma bond in between involves overlap of one of my carbon sp2s on the carbon on the left with the carbon on the right. Here's one of my carbon atoms with the nucleus right here. Here's the other carbon atom with the nucleus right there. The overlap of those two large lobes of the sp2 hybrid orbitals gives me my sigma bond. There's two electrons. The pi bond is formed the same way that we did in C double bond O. I have the plus lobe of the sp or the pz orbitals on each carbon atom lying above the plane of the molecule. I have the negative lobes in gray down below. These two orbitals overlap top to top, bottom to bottom, to form a pi bond. So really the bonding in C2H4 looks very similar to the bonding in CH2O. All right, so let's finish it up and see what the overall bonding structure looks like. So here was our orbital hybrid set. So I have my three sp2 hybrid orbitals in orange. I have my PZ orbital with its plus and minus lobes perpendicular to that plane. Here's what my sigma CC bond looks like. Here's what the pi bond looks like. Those two together form my C double bond O. Here are my hybrid orbitals. I have 1/3 2s, 2/3 2p to give me an sp2 hybrid orbital. So here's my Lewis structure. Let's see how we get that structure from valence bond theory. Looking at the sigma bonds all in the plane, here is one of my sp2 hybrids here. And notice that that overlaps with the 1s orbital of this hydrogen. Here's another sp2 hybrid orbital here. Now notice that I'm only representing these big lobes that are involved in bonding. I'm not showing these smaller lobes as make the drawing a little bit too busy. So those are there, but they're not going to participate in bonding. And my third sigma bond from carbon involves this sp2 hybrid orbital, which overlaps with the sp2 hybrid orbital on the other carbon. On the other carbon on the left side, I have the same thing here to form my CH single bonds that I had on the right side. The pi bonding scheme looks much like it did in C double bond O. So I have my plus lobes of the PZ orbital overlapping above the plane in purple, my minus lobes overlapping below the plane. These form the pi bond. So this is a 2-electron orbital, two electrons contained in the pi orbital, and then 2 electrons contained in the sigma orbital. And that's the representation of the 4 bonding electrons in this CC double bond. So once again, in general, a double bond is going to be formed from one sigma bond containing 2 electrons, sigma bonding orbital, and one pi bond, pi bonding orbital containing 2 electrons. Now just to summarize, we're going to look at more generally what happens with steric number 3. Steric number 3 means the central atom orbital hybridization, and in C2H4, notice I had 2 central atoms, here and here. Each of them has steric number 3. Steric number is just simply the number of atoms bonded to each of those central atoms, plus any unshared pairs of electrons. So each of them has steric number 3. But both have orbital hybridization sp2 because that's what goes with steric number 3. And also, all going with steric number 3 will be a bond angle set of 120 degrees. There was our same presentation for formaldehyde. Now, the exact same analysis is going to work for all these molecules as well. So here's the carbonate ion, steric number 3. I have 3 bonded atoms coming from the carbon with no unshared pairs. Here is my nitrate ion. Now I have a nitrogen central atom with 3 bonded atoms, no unshared pairs of nitrogen. This one I have 6 carbon atoms. And notice they're all identical, meaning they're all sp3 hybridized. Each one of these carbons has 3 atoms bonded to it. So the one to which I drew the arrow. The 3 bonded atoms are here. That's a carbon atom also. It's not labeled, should be. So carbon atom here. And then a carbon atom here. So there's my steric number 3 for that carbon. For this carbon here, the steric number 3 is these 3 bonded atoms. So all 6 of those carbon atoms have steric number 3, which means all 6 of them will have an orbital hybridization of sp2, and all of them will have bond angles of 120. Lastly, let's look at ozone, the O3 molecule. Now that consists of an oxygen central atom with a double bond to an oxygen on the left, single bond on the right. I have a formal plus charge on the central oxygen atom, a minus charge on the singly bonded oxygen atom on the right. Steric number is 3 because I have 2 bonded atoms, here and here. I have 1 unshared pair, steric number 3. That means the central oxygen atom in ozone has an orbital hybridization of sp2, bond angles of 120 degrees. So that ends our discussion of valence bond theory for steric number 3. We've done steric number 4 and 3 now in the 2 video sets.